Hello everyone, welcome to the course Data Structures. This is Thulasi Chitra, Associate Professor, Department of CSIT, MLR Institute of Technology. Let us see today's overview of today's session. Today we will be discussing about the other sorting technique, where we will be discussing about the heap sort. To know about the heap sort, first we need to see about what is heap introduction. What is heap and what is its introduction, we will look into that. Then we will be looking into what are different types of heaps we have. Then we will have the example of how to construct a max heap. Then construction of min heap also. Then we will see how we are going to perform max heap insertion and deletion. And at last we will see the implementation of heap sort. All these concepts we are going to cover in this today's session. First, coming to what is heap. Heap is nothing but it is a specialized data structure where it has some special characters, where it is going to tell you about the main two properties of heap. Heap is nothing but, just if you can see in general way, this is a heap. Right? We are going to see a diagrammatic way. This is nothing but a heap representation. Now, we are going to represent a tree data structure in terms of a heap. How that can be done? We have already seen what is a binary tree. In the same way, the binary tree, how we are going to represent that tree in terms of this heap representation. Okay. Now, the heap is nothing but a binary heap is called a binary tree with the following two properties. For a binary tree, it should follow the two properties mainly. What are the two properties it has to follow? The first one is the ordering property and the second one is the structural property. These two properties this binary heap has to maintain. What is this ordering property and what is structural property? Let us look into that ordering property and structural property. See the steps here. By this property, elements in the heap tree are arranged in the specific order. Suppose I have given some elements 2, 7, 9. Consider 3 elements I have given, and these elements we need to specify in the tree in a specific order. Suppose I am going to take the element 2. Right, this is one node, and immediately after that, if I want to insert another node, that should be inserted as the left of it. And if I want to insert one more node, and that should be inserted right of it. Why? Because a particular node consists of only 2 children. That is nothing but the property which it has to satisfy for a binary tree. Okay. And this is the specific order where we need to include. Suppose I want to insert one more element, consider 3, where I need to insert on the left of this one, we need to insert. If I want to insert one more element, 10, then on right of this it has to insert. If I want to insert one more element, 11, then we need to go for the right subtree and then we need to insert. Like this way, level wise we are going to insert. Okay, this is how the ordering is going to be. And this gives rise to two types of heaps. One is min heap and max heap. And we will be looking into what is min heap and max heap in the coming session. Coming PPTs we are going to discuss. This is about the ordering of the property which is going to be satisfied in binary heap. Now coming to the structural property. What structure it is going to maintain? Binary heap is an almost complete binary tree. Right, almost complete means we need to fill the nodes from left to right. Like this way, we need to fill the nodes from left to right, and you can fill from left to right, and you may have a node that can be left at the last end of it. Right, like this way, you may not have a node. Then also, it is nothing but an almost complete binary tree. And we will be discussing about different types of binary trees also in the next session, about when we are going to discuss about trees and the types of binary trees. There you will be getting some more clarity about this almost complete binary tree. Right. Here it has to maintain the property of almost complete binary tree. and it has all its levels completely filled except possibly the last level. What I said, this is the binary tree. If I am going to have a binary tree means each and every node have 2 children like this way, right? This is a complete binary tree. If I am not having this particular node, right, except possibly the last level, this is the last level, right? For this, if I am not having this node, then or this node, these 2 nodes I don't have, then it is nothing but a almost complete binary tree. And the last level is strictly filled from left to right. This one also, it has to be filled from left to right. That condition it has to follow, right? These 2 properties has to be satisfied by the binary heap or heap. Now coming to the types of binary heap. When you can see here, as we discussed previously in the ordering property, there we have 2 types of heaps that can be constructed. That is, depending on the arrangement of elements in the heap form or binary heap form may consist of 2 heaps can be constructed. One is max heap and another one is min heap. These 2 heaps we can construct from our given elements. Okay. Now coming to the max heap. Max heap conforms the properties of a heap. First, it has to satisfy the basic properties, that is ordering property, and another one is the structural property, right? In max heap, what happens? Every node contains greater or equal value element than its child node. This condition has to be satisfied by the max heap. Okay. Suppose I am going to have a node, for it is having some children. Whatever the node you are going to have here, that should be having a greater or equal element, okay, than its child nodes. Okay. This has to be satisfied. Thus, root node contains the largest value element. If I am going to place like this, if I am going to construct a tree like this, accordingly, this root node will be having the largest element. Okay. Let us go with an example. Consider the following example for max heap. This is the example. This max heap, what are the points we have discussed previously? According to that, whether this tree is not, we are going to verify. And this is a max heap or not also, we are going to check. Every node contains greater or equal value than its child node. And it is almost complete binary tree with its last level strictly filled from left to right. These 2 conditions, if it is going to satisfy, then we can say that it is a binary heap. That too, whether it is a max heap or min heap. This is a max heap where we are going to discuss, right? Now, you can check here the first statement. Every node, we need to check every node here. These are the nodes. You know, all these are nodes. These are the nodes, right? We need to check each and every node. Every node must have greater or equal value than its child nodes. Suppose if I am going to take this node 90, right? Its child node, observe whether it is greater than 89 and 70. Yes, it is satisfying our property. In the same way, check for the remaining. If I am going to take this node, its child node is 36 and 75, 89 is greater. In the same way here also, this is the node which I am going to take, 63 and 65, 70 is the largest. In the same way, if I am going to take 21 and 18, these are the child nodes, 36 is the largest. If I am going to take 15 I have, and every node is 75, 75 is greatest, right? If I am going to compare every node, the root node or parent node must be the larger one compared with the child nodes, okay? And one more, it must be almost complete binary tree. It has to fill from left to right. Level wise filling it has to be. and it should start from left onwards and it can end up to right. This is a max heap. Then coming to min heap, it is similarly we can say it is an opposite to it. Here also it is going to satisfy the same properties, but it is going to maintain. Min heap means minimum element should be there in the root. Okay. Min heap confirms the properties of heap, right? Every node contains lesser value than its child node. When I am going to take child nodes, its child nodes, when you are going to compare with the child nodes, the parent node must be a smaller node, and root node contains the smallest value, right? We can say this is just completely opposite to the max heap. You can see here the same thing. Here it is going to maintain these two cases. One is parent node is lesser than its child node. And another one is almost complete binary tree with which it has to fill it from the left to right. This condition has to follow it. And here if you could observe the example, this is my root node. If you compare all the elements here, all the elements which I have represented here, among all these the root node is having the smallest element, that is 10. Now compare each and every node here whether it is having the lesser element compared with the child nodes or not. Now see, now I am going to check this node with this children. These child nodes are what? 50 and 40. It is lesser than 20. If I am not, if I am going to check with this one 50, these two nodes are the child nodes, this is smaller, right? Like that way, if I am going to check with 30, these two nodes are larger when compared with 30. Like this way, it has to satisfy both the conditions. And another one is, it has to fill from left to right. Done. This is a min heap. Now, array representation of heap. How we are going to represent this tree, that is whatever you are going to construct in the tree form in terms of an array. We are unable to see the tree in our output, right? If I am going to execute some program also, I can't see this structure. This structure I can't able to show you. But this can be maintained in an array. Array representation of heap. Here, a binary heap is typically represented as an array. As we have seen, if I am going to do a program based on this heap also, I can't show this tree representation as my output. But how we can see the output? In terms of an array, we can store and we can see the output. Okay. If I am going to have an binary heap representation like this, how this will be represented in terms of an array? Let us see. If I am going to start its indexing from 1, 2, 3, 4, 5, 6. Level wise we have given the values, right? In the same way, if I am going to see here in the array normally starts from 0 onwards, but here I have represented it from 1. If I am going to start from 0, you can start from 0 indexing here. Okay. In one index, I am going to store the value of A, in index 2, B, index 3, C, and index 4, D, 5, E, and 6, F. Like this way, based on the indexes, we have stored the elements. But we have some logical thinking here. Based on its levels of tree, we are going to store it in the array representation. What is happening here? Let us look. A binary heap is typically represented as an array based on its indexes. Indexes are index where it is going to starts with 1. If I am going to start with 1, we are going to have these formulas can be used for finding its where that particular element index is. If I am going to start with 0, it will be having a little bit of change. Okay, let us go with the 1 itself, and no need to have any confusion over here. Okay, if index starts from 1 onwards, if its parent node will be present at array location, its parent node will be present at its array location. Please see the statement, array of I by 2. I is representing its index, starting index, you consider. Okay. Suppose array of I by 2, this is nothing but the seal value, right? Seal and floor, both values are there. Here we are going to take the floor value, sorry. This is going to represent the floor value. Based on this, we are going to see where the particular node is present according to the index. Okay. Let us see array of I by 2. This will be representing the parent node, and we can able to find the child node also. Its child node will be presented at array location array of 2i, and the right child node will also be present at array of 2i plus 1. Let us take some example here, and based on that you could understand how we can identify where is our parent node, where is our child node, and where is our left child node and right child node also. Okay. Now we are going to represent in the array index format. If I am going to have my elements in the array format, now I need to identify the node D, whether it is a left child or right child, or whether it is a parent. I need to identify. I am going to store the elements in the array. Now from this I am going to identify. Now D is at which index? Index number 4. Right? Now what is my I value? I value equal to 4. Okay. I value equal to 4. First apply for parent's node. What is the parent node? Array of 4 by 2. Array of 4 by 2 is nothing but you are going to get the 2 value. You are going to get the 2 value, that is the parent node. Okay. This is representing the parent node. Now I am going to take my I value. So now this is the parent node. Now based on this parent node, I am going to check 2 into, if it is of left child or right child, I am going to check it. 2 into I. 2 into I means I is nothing but the 2 value, that is nothing but 4. Now if I want to check it as the right child, 2 into I plus 1. I is nothing but 2 plus 1. This is nothing but 4 plus 1. This is 5. Now according to this, now we can able to construct a tree and we can check it. 2 is nothing but the parent node. 2 is nothing but the parent node. Yes, B is the parent node. And left child of it, what is the index it is representing? 4. Left child of B is D. That is 4. If I am going to check with the 4 or D, based on the parent I can identify which is my child, left child, and which is the right child. And 4 is representing the left child, its node name is D. And what is the right child of it? E is the right child. If I know the parent, from there I can identify which is the left child and which is the right child. Okay. Now suppose I am going to take C as my parent. Parent index is 3. And what is its left child and right child, I need to identify. Okay. Let us look into this so that you could understand some more clearly. P equal to 3, that is a parent node, I am considering it as 3. Now what is the left child and right child for it? What is the left child? 2 into I, array of 2 into I. 2 into I is nothing but 2 into 3, 6. And right child is 2 into I plus 1, that is 2 into 3 plus 1, 6 plus 1, that is nothing but 7. If I can check that here in the tree, F is the left child and we don't have any index 7 for the right child. Okay. From this we can identify this is the parent and this is the child, that too left child. If I have one more node here, then consider it as E of G, then this one is representing the right child. From the parent node we can identify which is the left child, which of the elements are having the left child and right child. Thank you.